In Robotics 1, we focused almost entirely on learning how to position the end effector of the robot. But in practice, we don't only care about the end effector position, we also care about how fast the end effector is moving. This is especially important for applications like robot painting, welding, and other manufacturing, for example, because in these situations, the speed of the end effector has a big impact on how well the painting, welding, cutting, or whatever job comes out. Today, we're going to do the hands-on portion of the class first because it will help you understand why the Jacobian matrix is important, and it will set us up for writing in the Jacobian matrix equations to control the velocity of the end effector in the next class on path planning. You should already have your SCARA manipulator built here like this. Open PSA Creator, and we're going to write some code to control the velocities of the servos. I'm going to create a new project in a new workspace, and I'm going to call the workspace Robotics 2. If you already have a workspace that you created for Robotics 1, you might want to create this project in that workspace instead. I'll name this project Jacobian. First, we'll rewrite some code to set the angles of the servos. In the top design, I'll add one PWM block and rename it servos. It will have two outputs. We learned in Robotics 1 that these servos are controlled by a PWM signal where the pulse has to have a period of 20 milliseconds. We also learned how to calculate what settings would get us the required period. If you'd like to review how we did that and you're watching this video through roborock.com, there's a link next to this video that points to that other video. For now, let's just set the settings that we learned in that previous video. I'm going to change this to 16-bit and the period to 60,000 and click OK. Then we'll go get a clock from the System menu and wire it to the clock input. Then we'll go back up to the Digital menu and then Logic and get a logic low and wire it to reset. I'll double click on the clock, change its frequency to 3 megahertz, click OK, and then we'll check the settings in the PWM and we see that the period has become 20 milliseconds. Now I'll set the two compare values both to 0 so that the servos will by default do nothing, and then click OK. Next, scroll down to the Ports and Pins menu and get two digital output pins and wire one to the PWM1 output and wire the other to the PWM2 output. I'll rename these two pins Servo 1 and Servo 2. Next, let's take a look at our pins. We'll pick two pins to plug our servos into. Click on the port drop-down. I'm going to use pin 16 for servo 1 and pin 17 for servo 2. Now go to main.c. I'll delete the comments. If you have an error here, don't worry about it yet. We always get an error here by default before we've built the code for the first time. I'm not going to use any interrupts, so I'll delete these lines here. I'm going to take these two functions that we developed previously in Robotics 1 and put them in here. As a reminder, each of these functions takes in an angle in units of degrees, and it returns a compare value for the PWM signal in units of ticks of the timer. It does this conversion by using the 2-point line formula to convert between a min and max angle in degrees and a min and max number of ticks of the timer. We can tune the servos a little bit by adjusting these min and max tick numbers to change the angle which corresponds to the min and max angle and the angles in between these two. Now, right now we have it set up so that the minimum angle of servo 1 is 0 degrees and the maximum angle of servo 1 is 180. And the minimum angle of servo 2 is -90 and the max angle is +90. For now, I want to change this. So I want to have the minimum angle of servo 2 to be 0 and the max angle 180. Also, I'm going to start by setting these minimum and maximum ticks to 1500 and 6500 for both of these servos. In a moment, we'll tune these to get them a little more accurate. Now, down here in main, the first thing we need to do is start the servos. So I'll type in the name of my PWM block, which is servos, and then underscore start, open and close parentheses, semicolon. Let's go ahead and build this code just to make sure that we haven't made any errors yet. Wait until this build succeeds, and if you have any errors, solve them now before we go on. So your first function should look like this, and your second function should look like this, and the rest of your code should look like this, and hopefully you got build succeeded down here. Now we'll write some code to set the angles of the two servos. Inside the for loop, we'll do servos right compare 1. Right compare 1 will be for the first servo, and right compare 2 will be for the second servo. Then we'll call the function theta1, and we'll give it the input 0.0 degrees. Then we'll have a little delay in order to wait for this servo to get to its position. Then we'll do servos right compare 2, and now we'll call the function theta2 and give it the input 0.0 degrees, and then give 1 second for that servo to get to its position. Now plug in your PSOC and wire up the servos. The red wire should be connected to VDD. The black or brown wire, depending upon the colors of the wires on your servo, the black or brown wire should go to ground, and the white or orangish yellowish wire should go to the 2 pins that we set up here. So the white or orange wire for your first servo should be connected to pin 1-6, and the white or orange wire of your second servo should be connected to pin 1-7. Once you have that, we'll click program to program the PSOC. When I click program, this is the result. My first servo is turned a little bit too far negative, and my second servo is also turned too far negative. When I have this correct, it will be straight out. Now, if you run yours and it's nowhere near being straight out, first unscrew these two screws and rotate the horn, and then pop the horn back on and screw it down so that it's at least close to being horizontal along this, which is our x-axis, our x0 base frame axis. Now also, I can hear the servos buzzing. Usually when the servos buzz, that indicates that we're trying to get them to go to a position that's outside their normal range. So I'm going to go back into my code and make some changes. Back here in my code, I'm going to change 1500 to 1600 for both theta 1 and theta 2. And then I'll click program. My hope is that after this runs, the servos won't click anymore, indicating that they're not trying to go to a position outside their range, and that they'll be closer lined up with the x-axis. So this is the result after I changed 1500 to 1600. My two servos aren't buzzing anymore, but the first servo is still turned a little bit too far. The second servo, however, is lined up pretty well. For my first servo, I'm going to change 1600 to 1700 and try it again. I'm going to increase this number a little bit more until I get that first servo to really line up well. Alright, I settled on 1750 and 1600 for the minimum value of the two servos. The next thing I'm going to test is the 90-degree angle. I'll change these two values to 90 and then program the PSOC. At 90 degrees, the first servo should line up exactly with the y-axis, and the second servo should be straight out to the left at a 90-degree angle between this link and this link. So now I'm going to go back and adjust my top numbers. I need both servos to turn a little bit farther than they've turned so far, so I'm going to make this 6600 and this one also. That made a big improvement on both servos. I'm going to stay with this as my final tuning. Now, let's write some code to get the servos to move at a constant velocity. If we were using DC motors, this would be really easy. We would just have to change the voltage that we're providing to the motors. Because we're using these servos that have built-in position control, we're going to have to control the velocity by putting the positioning in a loop. I'll show you what I mean. First, I'm going to remove this for loop. Now, right after we start the two servos, I want to start by getting the two servos into a starting position. The starting position for the first servo will be 0. And for now, the starting position of the second servo will also be 0. I'm going to remove this first delay so that the moves happen at the same time. And I'm going to give a little longer delay here to let both servos get into position. Let's give 3 seconds. Now I want servo 1 to move through its whole range from 0 to 180 degrees at a constant velocity. So I'm going to go up and create a variable, a floating point variable, so that it has a decimal, and I'm going to just call this angle 1. I'll start out with angle 1 being equal to 0. Then I'll say while angle 1 is less than 180, I'll copy this line. We're going to set a new angle for the first servo, angle 1. Then we'll make angle 1 increase by some amount. And then we'll do a little delay. For now, I'm going to make the delay be a constant 100 milliseconds. Now we haven't declared increment or given it a value yet. Let's go back up to the top. Now, what value should I give to increment? Let's do a little test first. Let's set increment equal to 10. Then program the PSOC and watch what happens. Set increment to 1.0. Then program the PSOC and watch what happens. What we're seeing here is a controlled 1 degree per 100 millisecond motion of the first servo. The motion is jerky because we don't actually have direct control over the velocity of the motor inside the servo. So it's moving 1 degree per 100 milliseconds, or 10 degrees per second. At the end, the marker should be on the other side of the x-axis. If it's not anywhere near that, go back and adjust your numbers so that 180 degrees really does line up the first servo with the other side of the x-axis. One of the reasons for the jerkiness of the motion is the amount of time that we are delaying inside this loop. Let's make this delay be 10, and then we'll have to change the increment to 0.1 in order to achieve the same velocity. Program the PSOC and watch the motion. We didn't completely solve the jerkiness of the motion because we still don't have control of the actual velocity of the motor inside the servo, but this is much better than it was before. Now, can we write an equation to calculate increment based upon the speed that we want the motor to move? Back up at the top here, let's create a new variable called float velocity. And I'll put a comment here that says this is degrees per second velocity of the first servo. Now, to calculate increment, we need to do a unit conversion. Velocity is in units of degrees per second. But since our delay is only 10 milliseconds, we need to convert this to units of degrees per 10 milliseconds. I could get that by simply dividing this number by 100. I'm going to put 100.0 here because I want increment to end up being a floating point value. That is, a value with a decimal, not an integer. We always have to be very careful that we only put integers, numbers without a decimal point, when we want the result to be an integer. Now we can set the value of velocity in units of degrees per second. Let's say velocity is equal to 10 degrees per second. Program the PSOC and watch what happens. Since the move goes 180 degrees, if you're really moving 10 degrees per second, it should take 18 seconds to make the move. Try to move 10 times as fast. Program the PSOC and watch what happens. This time, it should have made the complete move in 1.8 seconds. If this is working for you, it's time to do the experiment that we want to do today to help introduce us to the Jacobian matrix. Run this code again and watch what happens, but this time pay close attention to the speed that the tip of the marker is moving. You might want to remove the cap of the marker to watch. Can you figure out how fast the tip of the marker is moving in units of centimeters per second? Now, change this number to 140 so that theta 2 starts at its 140 degree position instead of its 0 degree position. Program the PSOC and watch the motion again. Pay close attention to the speed of the tip of the marker, that is the end effector. Do you notice a difference? When we start out with theta 2 equal to 0 degrees, the tip of the marker moves much faster than when we start out with theta 2 equal to 140 degrees. In other words, the relationship between the velocity of the end effector and the velocities of the joints is different depending upon the values of the joint variables. If we want to be able to control the velocity of the end effector, we not only need to pay attention to what the velocities of the joints are, but we're also going to need to pay attention to what the values of the joints are at any point in time. Now, it turns out that we actually do have a nice, easy way to do this kind of a calculation where we figure out the velocities of the joints that will get the end effector to move at the right velocity, taking into account the position of the manipulator at each point in time. This calculation is called the Jacobian matrix. The Jacobian matrix is a matrix that relates end effector velocities to joint velocities like this. Okay, so what does this mean? Let's start on the left and think through what this equation means. On the left is all the stuff that describes what's happening with our end effector. The dot notation refers to a derivative in time. So x dot means how fast the end effector is moving in the x direction. Here, the x, y, and z directions are measured in the base frame. So in our SCARA setup, x dot means how fast the end effector is moving off to the right. Similarly, y dot and z dot say how fast the end effector is moving in the y and z directions of the base frame. Okay, so what do these next three elements mean? Omega x, y, and z. These parts say how fast the end effector is rotating around each of these axes. For example, watch what happens with the marker as the servo moves. Before the movement starts, part of the label of the marker is pointed to the right. And after the movement, that same part of the label of the marker is pointing to the left. So during the motion, the marker has rotated around the z-axis. This thing here, omega z, says how fast the end effector is rotating around the z-axis during the motion. Similarly, omega x says how fast the end effector is rotating around the x-axis, and omega y says how fast the marker is rotating around the y-axis. Now, note that with this SCARA manipulator, there is no way to get the marker to rotate around the x-axis. To do that, we would have to be able to rotate the marker like this. We also can't get the marker to rotate around the y-axis. To do that, we would have to be able to rotate the marker like this. Okay, next we have this J. That's the Jacobian matrix, which we'll look at in depth in the next video. For now, let's look at these mysterious Q's here. You know that we use the letter theta to represent the rotation of a revolute joint, and we use the letter D to represent the extension of a prismatic joint. Well, we use the letter Q to refer to a joint when we don't yet know whether it is a revolute joint or a prismatic joint. So if our manipulator is all revolute joints, we'll replace these Q's with thetas. If our manipulator is all prismatic joints, we'll replace these Q's with D's. If we have 2 revolute joints and 1 prismatic joint, we'll replace the first 2 Q's with thetas and the third Q with a D, and so on. Now, also, I just wrote a couple of Q's, then some dots, and ending with QN. The N here refers to the total number of joints that we have. So if we have 3 joints, we'll have only 3 Q's. And if we have 6 joints, then we'll have 6 Q's, and so on. Now, each of these Q's has a dot over it, so that means that we're looking at how fast the joint is moving. So if our first joint is revolute, this Q will become a theta with a dot, and the units of this thing will be radians per second, because it means how fast the joint is moving. If the joint is prismatic, we'll replace the Q with a D with a dot, and the units will be meters per second. Okay, the only part of this equation we haven't yet looked at is the actual Jacobian matrix itself, represented by this capital letter J. If we can find this matrix, we will know how the end-effector velocities are related to the joint velocities, and that's our main goal here. So in the next video, we'll look at how to find this Jacobian matrix.